Okay.
Okay, so maybe I introduce you. So welcome everybody to the second talk of today. We have Perla Sousi from Cambridge. We'll talk about the four-dimensional uniform spanning tree. Thank you.
Okay. So thanks a lot for the invitation. It's a great pleasure to speak at this venue. So I'm going to talk today about the four-dimensional uniform spanning tree, and this is joint work with Tom Hatchcroft. So since Sarai already defined what is a uniform spanning tree and so on, I'm not going to spend too much time on this background stuff because I expect most people must have been on her talk as well. So, okay, but just to fix notation, if we have a finite graph G, then first of all, a tree is a graph with no cycles, and the spanning tree is a subgraph of the graph, which is a tree and spans the graph, so the vertex set is V. So now if we have a finite graph, we can count all spanning trees. It's a finite collection, and we can pick one of them at random, and this is what we call the uniform spanning tree, and we give equal probability to all trees in the collection, graph T. And I will abbreviate this as UST. So this is a portion of the uniform spanning tree of Z2. Sarai already defined what we mean by a uniform spanning force measure in higher dimensions, but I'm also going to talk about this a little bit because I want to explain some things that were not in her talk. So now I just explained what we mean by uniform spanning tree of a finite graph. Here we have an infinite graph. She already explained that one can take weak limits. But another way to think of it is if you take a large ball, then what you see in this ball, if you take the restriction of the uniform spanning tree of the whole of Z2 in the box, it's very similar to what a uniform spanning tree of the box would look like. So I just want to say that the first one who studied uniform spanning trees was Kirchhoff in the 1850s. So everyone has heard of Kirchhoff because of his foundational work on electrical networks. And it is in this paper in 1847 where he developed a set of rules that formalize that current and energy are conserved in electrical circuits. And this is where the connection between uniform spanning trees and effective resistances was established. So what he showed is that the effective resistance of an edge E is equal to the ratio of the number of spanning trees that contain E divided by the total number of spanning trees, which means that the effective resistance of E is equal to the probability that E belongs to a spanning tree picked at random. Another thing that he proved in his paper is the matrix tree theorem, which counts the number of spanning trees of a graph in terms of the Laplacian of the graph, where you delete one row and one column. Okay, so when we define a random object, the first question we might want to ask is, how can we sample such an object? So if we have a finite graph, then there are a few algorithms. The first one goes back to Kirchhoff using the matrix tree theorem, because it counts the number of spanning trees, so this gives you immediately a way of sampling one. Then another algorithm is Wilson's algorithm using loop-raised walks that Sarai already introduced. And so I'm just going to review it very quickly. And then there is another algorithm due to Aldous and Broder, and they both acknowledge discussions with Percy Diaconis. I'm going to talk about this algorithm, and both Aldous and Broder define this algorithm for finite graphs. So what I will do later is I'm going to describe an extension of this algorithm to the infinite transient case, which was done by Tom Hatchcroft during his PhD. And I'm going to describe this because this is one of the important ingredients of the proof of our main theorem that I will state. Okay, so Sarah already spoke about loop-erased walk, so very quickly to review it, if you have a finite path, you can define the loop erasure by erasing loops in the chronological order in which they appear. And now if you have a simple random walk path, if it is a transient path, this procedure is well defined because this random walk will visit every vertex finitely many times, so we can define the loop erasure. In dimensions where the walk is recurrent, it's not so clear how to define the loop erasure, but one can do it by simply taking the walk up until it exits the ball of radius n, erasing loops, and then taking the limit. And this is the red curve, the limit is the red curve that you see here, which is an SLE2 curve. Okay, so let me quickly review Wilson's algorithm. So we have a finite graph, we fix a root vertex, we order the remainder of the graph, and now we start a simple random walk from the first vertex in the ordering, we run it up until it hits the root, we erase loops, then we start a random walk from the second vertex in the ordering, we run it up until it hits the path that we obtained before, after erasing loops, we erase loops again, and we continue until we use all of the vertices. So this clearly constructs a spanning tree, but what is remarkable is that the tree that we get has the distribution of a uniform spanning tree. So this is what David Wilson proved. So it's clear how to generalize this algorithm to an infinite recurrent graph. So we just fix the root vertex, we order the rest, and we just do the same procedure. And this is going to produce a connected tree because the similar random walk concept is recurrent, so it will hit every vertex with probability 1. And this is the same picture that I showed earlier. The reason, so this, we call it the uniform spanning tree for the reason I mentioned earlier, that on large boxes, it looks similar to what a uniform spanning tree of the box would look like. Okay, so now if we have an infinite transient graph, how should we define it? So as Sarah already said, we know how to construct a uniform spanning tree on a finite graph. So we can just take an exhaustion of our graph, let's say by boxes, and then using the connection to electrical network theory, it's not hard to show that the sequence of measures μn converges weakly as n goes to infinity to a limiting measure. And we call this limiting measure the uniform spanning forest measure on ZD. Because since it is the limit of the uniform spanning tree measures, it's going to be supported on graphs with no cycles. And a priori, we don't know whether the resulting graph will be a forest or whether it would be a connected tree. So the first question that arises is whether this is connected. Sarai already told us that it is a tree, almost surely if d is less than or equal to 4, and it consists of infinite many trees if d is greater than or equal to 5. So I just want to say something about this theorem. So this result shows that dimension 4 is the critical dimension for the uniform spanning forest measure. So let me take a step back. So Pimantel proved this theorem in 91. 10 years later, Benjamini, Lyons, Perens, and Schramm generalized Wilson's method for finite graphs to the infinite transient case, and they call this algorithm Wilson's method rooted at infinity. So the way that this algorithm works is in the recurrent case or in the finite graph, at time 0 we start with just a single vertex with a root, and then we construct the parts of the tree in the way I described by running loop erase walks from all of the other points of the graph. Now, for Wilson's method rooted at infinity, the difference is that we start at time 0 with the empty forest, and then we start a simple random walk from the first vertex of the ordering, and we run it forever. Because it's a transient graph, we can loop erase this random walk path, and then we keep the path that we get in our collection. Now we start another simple random walk from the next point in the ordering, and we run it either forever or until it hits the first part that we have already constructed. And it turns out that this algorithm gives the correct distribution of the uniform spanning forest. The way I want to describe it is because with this tool, this theorem of P-Mangley, so P-Mangley didn't have this algorithm when he proved this theorem. But with this theorem, the question of whether the uniform spanning forest measure is connected or not, it reduces to the question of whether a loop-erased walk and an independent simple random walk intersect or not. So let's look at the question of two independent simple random walks intersecting, because it is easier than a loop-erased walk and a simple random walk. So suppose that you have two independent simple random walks in dimension D. Now, if you count the total number of intersections, you will see, just using the local CLT, that this number is infinite in dimensions 4 and below, and it's finite in higher dimensions. So this shows that dimension 4 is the critical dimension for the number of intersections, in the same way that dimension 2 is the critical dimension for the question of recurrence. So intersections in dimension D correspond to collisions in dimension D minus 2. You get exactly the same growth. Okay, so if you look at the total number of intersections of two independent walks in dimension 4, if you run one walk up to time n, this is going to grow like log n, which is the same as the total number of collisions in dimension 2. And dimension 4 is the critical dimension because of this log. So in higher dimensions, the number is finite, independent of the dimension, and in lower dimensions, it depends crucially on dimension. So I'll come back to this criticality when I state our theorem. Okay, so now we know that the uniform spanning forest is a single tree in dimension 4 and lower, and infinite many trees in higher dimensions. So now I would like to understand the geometry of the trees better. So in order to do that, I'm going to introduce the notion of one-endedness. So if we have an infinite tree, we call it k-ended if, starting from every vertex, there exist exactly k distinct infinite simple paths. So I just want to emphasize that here I say distinct, I'm not saying disjoint. So this path could be like, so these are two infinite paths. If they both continue, they have the same first common part, but they are distinct eventually. So an infinite tree is k-ended if, starting from every vertex, you can find exactly k distinct infinite simple paths. So obvious examples, the line of integers is a two-ended tree, while the natural numbers is one-ended. So now the question is, what can we say about the trees of the USF? So this was proved by P-Mangley in dimensions 4 and lower. So he showed that all trees in the USF are one-ended for all d less than or equal to 4, and he proved that in higher dimensions they are at most one-ended. And then Benjamini, Lyons, Prince, and Schramm, in the same paper I mentioned earlier, they completed the picture by showing that all trees in the USF are one-ended for all dimensions. So D has to be greater than or equal to 2, because of course in dimension 1 you just get the whole line, which is obviously two-ended. Okay, so now that we know that all trees are one-ended, the next step is that we want to quantify this one-endedness. So what do I mean by this? So I'm going to define the notion of the past of 0. So I define the past of 0 to be 0 together with the finite piece that you get when you disconnect 0 from the tree. So suppose here is 0, and this is the tree where 0 belongs. So in dimensions 4, we'll be interested in its the whole USF is a tree, but let's just look at the tree that contains 0 in any dimension. Then from the previous theorem, we know that this is one-ended. So starting from 0, there is going to be a unique infinite ray. So this is the green path that I drew here. And all of the other paths are going to be finite. So the past of 0 is this finite path that you get if you disconnect 0 from the tree. Okay, so this is how we define the past of 0. I'm going to give an equivalent definition in a little bit of the past, where I will introduce orientations on the edges of the tree. But the past of 0 is just defined to be the finite part that is hanging off the tree when you disconnect 0 from the tree that contains it.
I assume that the name past is coming from the oriented thinking, right? You're thinking of somehow flowing along as time passes, something like that? Why past?
So I'm not sure actually why it's called past, because with the algorithm that, even with the algorithm that I will define later, it's actually something that is created later. Yeah, I don't know why it's called past. I think it was first introduced, okay, I could be wrong, but I think it was first introduced in a paper by Lyons, Morse, and Schramm. It could have been introduced earlier as well. Okay, so maybe it could be because of the direction. So, okay, so let me just say briefly. So if you have, we have a one-ended tree. So we have, from 0, we have a unique infinite path. So there is a way to assign orientations to the edges in such a way that there is a unique oriented edge emanating from every vertex. So if you add orientations here, we are going to put here the arrows going in this direction. And then for the past, the arrows will be pointing towards 0. So maybe it's called past for this reason. I'm not entirely sure. So I'm going to define the past later as the set of vertices that have a directed path towards 0. And the forward path, we're going to call it the future of 0. So it's the set of vertices that 0 leads to. There is a directed path starting from 0. Okay. So if the definition of past is clear, then I'll mention the result of Tom from 2017. So Tom looked at dimensions d greater than or equal to 5, and what he showed, so as I said before, what we want is to quantify this one-endedness. So we want to understand how large the past of 0 is. So when I say how large, I mean in the following sense. So first of all, we want to understand the intrinsic radius of the past. So what is the probability that the intrinsic radius is at least n, which means what's the probability that the past of 0 contains a path of length at least n. So what Tom showed is that this is up to constants 1 over n. Then
I'm gathering that there's no point in asking for the expected size, right? It's too large.
Yeah, that's right. So you will see it here. So I'll get to the size. So the probability that the past of 0, the extrinsic radius is at least n, this grows like 1 over n squared. And the probability that the volume is at least n is up to constants 1 over root n. So let me just say that when I write this symbol here, I just mean that there exists universal constants C1 and C2, so that this probability is upper bounded by one constant times 1 over n and lower bounded by the other constant times 1 over n, the same. So I'll be using this symbol quite a lot in the talk. And as I said, Tom proved this result for dimensions 5 and higher, but he also proved it for more general transitive graphs, as long as they have quintic volume growth, and for some other classes of graphs. Now, so this is a type of universality result in the sense that these exponents here do not depend on the dimension. So what this is saying is that dimensions 5 and higher behave in a mean-field way, and they don't depend on dimension. So then the question that arises is what happens in dimension 4. And as I said before, dimension 4 is the critical dimension for this model. So
I may have missed something, but when you're talking about the past, in higher dimensions higher than 4, you're looking at the connected component of 0, right?
Yes.
Because you don't have the whole, space, you just have a connected component.
That's
Right?
right. So I just look at this part here. So so I look at the tree that contains 0, because if we are in higher dimensions, it's going, so suppose you are in dimension 5, you're going to have infinite many trees. So then you just look at the tree that contains 0.
Yeah, so you're missing most of the space in dimensions higher than 5. In dimension 4, you're
Yeah.
seeing the whole space. Okay.
So you're not looking at the future or these parts that are hanging over the future here.
Sure, but you're selecting, when you're talking about past and future, you're selecting a tree. Yeah, I mean, you're selecting within a tree. And for
Yes.
dimension 4, the tree is the whole space. And for dimension 5,
sure. Yeah, sorry, I misunderstood the question. Yeah, that's right. Yeah. So that's right. So in dimension 4, it's the whole space. The tree is everything. So, and we define the past, of course, in the same way. Yeah, that's right. I'm sorry. So, okay, so I said before the dimension 4 is the critical dimension for this model. What this means is that we would expect to get the same scaling here as in the mean field case, but we expect logarithmic corrections to this mean field scaling. And what we managed to do with Tom is to calculate the exponents of these logarithmic corrections for dimension 4. So this is our theorem. So the probability that the intrinsic radius is at least 10, we saw that it's corrected by this log n to a third term. Now the probability for the extrinsic radius to be at least n, we get log n to the 2/3 plus a little of 1 term here. So the little of 1, what it means is that for every epsilon, there exists a constant c epsilon, so that the probability that the past reaches the boundary of the ball of radius n is at most log n to the 2/3 plus epsilon times a constant that depends on epsilon. So this little of 1, we only lose it in the upper bound. The lower bound, both for the first and the second tail probabilities, you don't get the little of 1, and there are the easy directions of these theorems.
Perla, can I ask a question? Oh, sorry.
Yes.
How can it be that, a stupid question, how can it be that the containing a pass has a larger probability than hitting the boundary? Isn't it the case that if you contain a pass of length n, then you will hit the boundary? The inclusion here is not clear to me, no? If I have a pass of length n,
yeah,
then I necessarily include the boundary. So the probability of I hit the boundary, no?
Well, the length is a number of vertices, I guess, so you don't have to. It can all go back and
yeah, that's right. Yeah, okay, that's right. Yeah.
You
so
cannot create loops. It's a pass, right?
yeah,
so,
but it could be like this.
Yes.
So this
I
could
see.
have length n, but it doesn't hit the boundary.
Okay.
Yeah. So in the first part, we look at the. So that's right. I said it's the intrinsic radius. So we count distance on the past, not the Euclidean distance. Okay. So and the final result is the probability that the volume is at least n is up to constants log n to 6 divided by square root n. So what I'm going to do in the remainder of my talk is I'm going to explain some of the ideas behind the proof, and I'm going to explain where these powers come from, the log n to a third. So first of all, I want to say that we use the same strategy as Tom used in higher dimensions. So we're going to use his extension of the Aldous-Broder algorithm to the infinite transient setting. But as I will explain, things become much more delicate in 4 dimensions, and I will explain exactly what we had to control in 4 dimensions. So the proof relies heavily on this generalization of the Aldous-Broder algorithm, and also on the non-intersection exponents between loop-erased random walks and simple random walks, which was established by Lawler in the 1990s, I think. Okay, and the other thing I want to say to repeat is that the lower bounds are the easy directions in both these tail probabilities. So what I'm going to do is I'm going to give an almost complete proof of the lower bound for the intrinsic radius, because this will illustrate the method. And then I will explain just at a high level how we prove the upper bound. And I just want to say that an important ingredient is to prove the first tail probability, and then the other 2, they still require work, but they use the intrinsic radius as an important ingredient of the proof. Okay, so if you're all happy with the definitions and the statement of the theorem, I can move on to the Aldous to tell you about the Aldous-Broder algorithm in the finite setting, and then how Tom generalized it to infinite graphs. Okay, I don't see anything in the chat. Okay, so as I said before, the Aldous-Broder algorithm is another algorithm for generating a uniform spanning tree of a finite graph. So let's say that we have this graph here on the right, and let's say that this is our vertex O. We just fix a vertex. It doesn't matter which one. And we start a simple random walk from here, and we run it up until it hits everything. It visits every vertex at least once. So we run it up until the cover time. Now, for every vertex, which is not the vertex O that we started with, we are going to keep the edge that was used. We're going to look at the first time that we hit this vertex. And in our collection, we're going to keep the edge that was used when we visited the vertex for the first time. So let me show. So we started from the center. Let's say we went down. First time we visited, we include the edge. I painted green. We went up, first time green. First time, we went back down, nothing happened. Down because we already visited the vertex. First time, back here. Now we went to the root, we don't do anything for the root. Then we went back up. This vertex was already visited, so we don't include this edge. And then we went to the left, and it was the first time it was visited, we painted green. This is the cover time, so we stop. And now all of the green edges give us a spanning tree. It's obvious by construction that what we get is a spanning tree. What is not obvious is that it has the correct distribution. So the tree that we constructed is indeed a uniform spanning tree of the graph G. So the proof of this actually is like a page or 2 long. So let me just explain how it's proved. So one defines a Markov chain on the space of rooted trees. So you have a Markov chain on the space of trees times vertices. So for every tree you consider it to be rooted, so you also distinguish one vertex. And then from every rooted tree, and then you define a Markov chain on this space. It's kind of a natural Markov chain to consider. And then you show that the invariant distribution for the tree component is the uniform distribution on the set of spanning trees. And then the theorem is proved by showing that the distribution on the spanning tree that you get by running this algorithm is the same as the invariant distribution of this Markov chain, and so it has to be the uniform measure. Okay, so this is how Aldous-Broder works for a finite graph. Now, it's clear how to generalize it to an infinite recurrent graph because you just run the walk forever. It will visit every vertex with probability 1, and then you apply the same procedure. For every vertex, you take the first time that was visited, and you look at the edge that was crossed when this happened. And this has the correct distribution. So now how can we generalize this to an infinite transient graph? So this is what Tom did. So his idea, so since in a transient graph, if you just run one walk forever, it won't visit everything. It's not clear how to immediately generalize it. So Tom's idea was to replace the single walk that is used in Aldous Broader by a Poissonian collection of walks. So when I say Poissonian collection of walks, what he did was to replace the single walk with the random interlacements process, which was introduced by Snitman in 2000 in order to study the trace left by a simple random walk in ZD in transient dimensions, and also afterwards it was generalized to other transient graphs by Augusto Teixeira. What is the random interlacements process? As I already said, it's a Poisson process. So one way to think of it is as a Poisson process of bi-infinite random walk trajectories that arrive in time. So it's a Poisson process on the space of paths times time. So paths in our space multiplied times time. So if you have a Poisson process, in order to fully define it, you need to specify the intensity measure. So I'm not going to write down the intensity measure here because it would take some work, but I just want to say what is the important property of interlacements that we're going to use, which is that if you have a finite set K, so say that this is K, a finite subset of ZP, and suppose that these are our random walk trajectories, these blue trajectories arrive in time, then the probability that we haven't hit K in the interval 0t, this is given by e to the minus t times the capacity of K. This is the important property of interlacements that we're going to use. So what is the capacity of K? The capacity of K, if K is a finite subset of ZP, is defined to be the sum over all points in K of the probability starting from X that you never hit K again. So this is how we define the capacity in the discrete setting. And this is the discrete analog of the continuum capacity, which is otherwise called the Newtonian capacity. So if you have a compact subset of RD, then the capacity is defined to be the inverse of the infimum here of this integral, where we take the infimum over all probability measures mu supported on A. And GXY is the green kernel for Brownian motion. We are in transient dimensions here, so this is well defined. And you can also write down this variational characterization formula in the discrete setting, where you replace GXY by the green kernel of simple random walk. So the expected number of visits to Y starting from X when you run the walk up to infinity. Okay, so what I did so far is I want to generalize the Aldous Broader algorithm to the infinite transient setting. I said that Tom's idea was to replace the single walk with the random interlacements process, and I stated the important property of random interlacements that we're going to use. So now let me tell you how to generalize the Aldous Broader algorithm in the infinite setting. So this is what Tom did is to define a Markov process on the space of spanning forest of ZT. So what do I mean by this? Let's take T in R and X in ZD. Okay, so I'm going to define sigma T of X to be the first time after time T that X is hit by a trajectory of random interlacements at time S. So we have our point X, and now we are looking after time T. So we have this Poisson process of trajectories that arrive in time. And we look at the first time after time t that x was hit by a trajectory. So this is sigma t of x. It's the first time that x was hit. And now I write et of x for the edge used to enter x at time sigma t of x. So let me just draw it. So suppose this is, let's say that x is here, and suppose that this is the first trajectory that hits x. Then this trajectory is going in this direction. And so the edge that was used when we hit x was this green edge here. So this is my et of x. So for every vertex, we look at the first time it was hit by some trajectory after time t, and I take et of x to be the edge that was used when visiting the vertex. Okay, and now, so as I said before, we can assign orientations to the, so because we have one-ended trees, we can assign orientations to the edges of the tree or of the forest in such a way so that every vertex has exactly one directed edge emanating from it. So what I'm going to do now is I'm going to set calligraphic ft to be the set of et of x, all of these edges where I reverse the direction. So et of x was crossed in this direction, so I take the opposite direction now. And you will see why we have to take the opposite direction. So I consider the set of edges et of x with the opposite direction over all x in ZB. So now this gives us an oriented spanning forest. So it is, when I say oriented, I mean that every vertex has exactly one directed edge emanating from it. So this is why we take the opposite direction, because we visit every vertex for the first time exactly once, so then we have to take the opposite direction so that there is a unique directed edge emanating from the vertex. Okay, so it's clear that this is a spanning forest and it's an oriented one. Now, what Tom proved is that Ft has the correct distribution of a uniform spanning forest. So let me explain the idea of the proof. Actually, the proof is quite easy. The main ingenuity here was to use the random interlacements in place of the walk. Once you decide to do this, then to prove that Ft has the correct distribution follows easily by viewing random interlacements as, so another way to view random interlacements is by taking a finite exhaustion of your graph, let's say by balls. So we are in ZD, let's say we take balls of radius n centered at 0, and I'm going to glue the boundary of these balls into a single point that I call the boundary of n, the boundary n. And now I'm going to consider independent random walk excursions, a Poisson process of independent random walk excursions starting from this boundary point. Now, if you choose the parameter of this Poisson process correctly, then this Poisson process of random walk excursions from the boundary is going to converge to the random interlacements process on the whole of ZB. So that's another way of thinking of random interlacements as the limit of these random walk excursions from the boundary. Now, if you apply the Aldous-Broder algorithm to this finite graph here, when your vertex O becomes the boundary vertex, then you know that this is going to give you the correct distribution by the correctness of the Aldous-Broder algorithm in the finite setting. And so then, by taking the weak limit, you get the correct distribution in the infinite setting. So you get that indeed Ft is distributed as a uniform spanning forest. So now, I'm going to define the future, as I wrote earlier, the future of x in the tree ft is defined to be the set of v so that there is a directed path from x to v. This is how the future of x is defined, and the past of x in ft, and I'm going to write that past after time t of x, and this is going to be the set of v so that x is in the future v. So as I drew earlier, if we have, suppose this is x, all of this is the past, and this is the future. Okay, so that gives us an equivalent way of defining the past. Oops, sorry. Start from here, the future. And because we said that the tree is one-ended, there is going to be a unique infinite path starting from 0, and this is what we call the future. So because of the one-endedness, these two definitions of past are equivalent. Okay, so now let me just recap. I defined the random interlacements process, and the way to generalize the Aldous Broder algorithm using the random interlacements process is to fix, so for every time t, we look at the first time that a vertex was visited, we take the first edge that was used when x was visited, and we reverse direction. And this way we get a realization of the oriented USF. And what is very useful about this construction, as I said before, is that we obtain a dynamical way of constructing the USF. So we have this Markov process, FT, that has a lot of nice properties, and Tom has used this algorithm in order to prove a lot of other important properties of the USF. So here I'm going to explain why this algorithm is quite useful in establishing the tail probability bounds for the past. In particular, so the first thing I'm going to do is I'm going to give, as I said before, an almost complete proof for the probability that the intrinsic radius.
Sorry, can I ask a question about the construction?
Yeah, of course.
It seems that the same trajectory arrived in this partial random field is like a two-ended path, which seems contained in this tree. So why the tree is one-ended? Like why you?
Can you say that again?
Yeah, I was saying it seems like the first trajectory arrived in this Poisson random measure of trajectory is contained in this uniform spanning forest. And it seems that this trajectory is two-ended. And why this forest is only one, has this one-ended property.
Sorry, maybe my picture is bad. This part here is finite.
Yeah, I was talking about the construction above, like see if those trajectories are fulfilled.
Oh, I see. Okay, so I'll talk about the proof of the lower bound, and it will become clear to you how you don't get an infinite past. I will explain. So the point is that this is the first, okay, so maybe if I say the following, things might become clearer. So this trajectory that I drew here is the first trajectory that hits X. But if you take a point here, it doesn't mean that this is the first time that this point was hit. This point could have been hit by a trajectory arriving like this. So if you reverse directions on this path, so you get the past of X is going, so this part here could contribute to the past of X, but this must have been hit before by another trajectory which had priority, because every time you take the trajectories that arrived earlier in time. So let me talk about the lower bound, and maybe this will become clear. Otherwise, we'll come back to it.
Okay, thank you. I got it.
Okay, so I want to show the following lower bound. So I want to show the probability that the past of 0 after time 0. So this 0 here, it has the distribution of the USF, but I just want to illustrate how we use this dynamical way. So that's why I indicate it by 0. We want to show that the probability that this path has a path of length at least 10 is lower bounded by log n to a third divided by n. So this is my goal. Okay, so in order to prove this, I'm going to give, we want to show a lower bound, so it suffices to give a specific strategy that is going to construct a big past. So what is going to be my strategy? So first of all, let's take epsilon to be positive, and I'm going to set it later. So I'm going to define 3 events. So A is going to be my first event, and I'm going to ask that 0 is hit by a unique trajectory of random interlacements, a unique trajectory, call it W, of the random interlacements process in 0 epsilon. Okay, so let me draw W here. So let's say that this is W, and let's say that 0 is here. So W arrived in this direction. So this is the negative part of W, and over here it's the positive part. So this part here is the positive part, and the other one is the negative part of W. So as you mentioned earlier, it's the forward path of W that is going to contribute perhaps to the past. It may not contribute anything to the past, so we will see how this happens. So let me make this look a bit bigger so that it becomes clearer. Okay, let's say we have this trajectory. Okay, so now I'm going to apply the Aldous-Broder algorithm to this forward path W. So what do I mean by this? I mean that, so what is the Aldous-Broder algorithm? For every vertex, but only for this trajectory, the vertices that are lying on this trajectory, I'm going to look at the first time that they were hit by the trajectory and take the first entry edge. So starting from 0, we go like this, we stop here because the vertex in the intersection was already visited. Then I continue, I stop there, and now I start again and I continue. So I drew this green path. This is the result that we get when we apply the Aldous-Broder algorithm on W. And now I'm going to draw this pink path. I'm going to call it eta. So claim eta is a loop erased random walk on Z4. So what is eta? I apply the Aldous-Broder algorithm to W. I get this green set. And now it's not hard to argue that this green set is going to have a unique infinite ray, which is eta. And it's not hard to show that this eta has the correct distribution. I mean, that it's a loop erased random walk on Z4 starting from 0. I'm not going to explain this proof, but this is an easy argument. It actually follows from the one-endedness of the trees as well. So, okay, so we have now this loop erased random walk eta. Now I'm going to look at the first n steps of eta, so eta 0n. So let's say it's this path here. Because we reverse direction, here we would have to put the arrows like this. Now, it's not clear that eta 0n will be included in the past. So why isn't this clear? Because there could have been a trajectory that arrived before time epsilon, which hit this path, and because we give priority to earlier trajectories, so then this point here would have already been visited, so that would disconnect this path from the past. So it's not, so I think maybe this answers your question. This part of W is not going to necessarily contribute to the past. But as I said, I want to devise a specific strategy which will give me a large past. So I'm going to ask that this path eta is in the past, just the path eta 0n. So in order for eta 0n to be in the past, first of all, I don't want the negative part of W to intersect eta. So I want this to be the empty set because the negative part of W came first. So it would have had priority. So if this trajectory went and hit, then the path eta 0n would not survive in the past. So this is one event, and the probability of B is up to constants 1 over log n to a third, because here we are looking at the intersection between a simple random walk and an independent loop erasure run for n steps. And this result is due to Euler. Okay, so this is one thing we don't want to happen. So we want it to happen. I mean that we don't want to have an intersection. And the other event is that we don't want any other trajectory of random interlacements between time 0 and epsilon to hit this path eta. So eta 0n is not hit by any other trajectory of random interlacements in 0 epsilon. Okay. So if A, B, and C hold, then the path eta 0n survives in the past. So the probability from up here is at least the probability of A and B and C. Because if eta 0n survives in the past, then we're going to have a large past. And so now it remains to bound the probability of this intersection. So the probability of A, remember we have a Poisson process, and so we want 0 to be hit by a unique trajectory. So it's going to be epsilon times e to the minus epsilon, the capacity of 0. Now the probability of B is going to be 1 over log n to a third. And so, okay, here I'm not explaining exactly why we get independence, but this is not hard to do. I will say something about that in a minute. And now for C, if I condition on the path eta 0n, I don't want this to be hit by any other trajectory in the interval 0 epsilon. So by the important property of random interlacements here, this is going to be e to the minus e to the minus epsilon, the capacity of eta 0n. So if I condition on this path, I don't want any other trajectory of random interlacements in the interval 0 epsilon to hit it. So we're going to get this expectation here. So, okay, so this independence here, it's quite easy to justify, and I'll explain how. So what remains to understand now is this exponential here. So as I will explain on the next slide, the typical value of the capacity, so the expectation of the capacity of the first n steps of the loop pressure grows like n over log n to the 2/3. So if we were to substitute the capacity here by its typical value, And actually, it's not hard to show upper tail estimates for the capacity. It's not hard to show upper tail estimates for the capacity together with this event here. They correlate well enough. So in order to kill the exponential term here, we have to choose epsilon equal to log n to the 2/3 divided by n. And so if you substitute this epsilon, you're going to get exactly this lower bound that I wrote here. So this is an almost complete proof of the lower bound. This is the easy direction of our proof. Most of the work in our paper goes into proving the upper bound. So now I have 5 more minutes.
So can I ask a question?
Yeah, sure.
So for the event C, you don't actually need that there's no other path in 0 epsilon, but in 0 with whatever time the path W came. This doesn't give you any better correction? If you take epsilon.
So we get the correct order here, log n to 3 divided by n. This matches the upper bound, so that's good enough. But yeah, one could do things even more precisely, but this is just a lower bound and it gives a correct order.
Okay, thanks.
Why expectation of capacity has this form?
Yeah, okay, so that's what I'm going to explain now. So do I have 5 more minutes? Okay, so I'll just explain. Okay, so here I just put a slide with a lower bound in case I didn't have time to present it. Okay, so let me explain why the capacity has this form. So I defined the capacity before as this sum. Equivalently, the capacity can be expressed in this way as the limit of the probability time from x that we hit the set k divided by the green kernel. This is easy just using the last exit decomposition formula. So in order to understand the capacity of a set, so here the capacity of eta 0n, we have to understand intersection probabilities between loop erased random walks and simple random walks. So now let me take a step back and take 2 independent simple random walks in Z4 that start at distance root n apart. So what Lawler proved in the 90s is that the probability that x and y intersect when you run x up to time n, and remember you start them at distance root n apart, this is up to constants 1 over log n. So let me just say very, very briefly where the log n comes from. So one way to show that this probability that the 2 walks intersect is to count the total number of intersections. So the probability that they intersect is equal to the probability that the total number of intersections, call it I, is positive. And now a trivial equality is that the probability that I is positive is the expectation of I divided by the expectation of I given that I is positive. Now, if you start 2 walks at distance root n apart, the expected number of intersections when you run one of them up to time n is going to be order 1. So the numerator is going to be order 1. Now, in the denominator, if you condition the 2 walks to have an intersection, you can think that both of them start from this intersection point, and then you run them up to time n, and then using the local CLT, you get that the total number of intersections when they start from the same point grows like log n. So then you get the 1 over log n. The argument I gave is totally wrong because the denominator, you cannot treat it in the way I said, because if you condition on having an intersection point, there is no Markovian way of defining the first intersection time. But nevertheless, it does give the correct order and gives an intuition of where the log n comes from. Okay, so this is the result for 2 independent walks. Now, if you plug this in the formula for the capacity of the first n steps of the loop erasure, you get that this grows like n over log n. So now this is for 2 independent walks. We want to go back to loop erase walk and an independent walk. So now if you have 2 independent transient chains, x and y, this is a result by Lyman, Spence, and Schramm, who showed that the probability that x and y intersect is up to constant the same as the probability that the loop erasure of x intersects y. So one direction is obvious, of course, but the remarkable thing is that this probability here is lower bounded by the other probability times some universal constant. So now if we look at the first n steps of the walk and we loop erase it, so we just loop erase this finite path, that's not the same as I had before, then we're going to get that the expectation of the capacity is going to be n over log n. Now we want to relate this to the capacity of the first n steps of the loop erasure using the result that I mentioned earlier, that if you have n steps of loop erase walk, the probability that not intersect an independent simply random walk is 1 over log n to a third. We see that we need n times log n to a third steps of simple random walk to produce n steps of loop erasure. So if now we are interested in the capacity of eta 0 n, this is up to constants, the capacity of the loop erasure of x run up until time n log n to a third, and this is the same as the capacity of x up until this time. Substituting here, you get the n over log n to the 2/3. So this is how we get the typical value for the capacity. And in order to prove the lower bound, we had to establish upper tail estimates, which are quite easy to obtain. Now, the upper bound is the more delicate part, and the way we prove it is by proving this inductive inequality. So Q of n is the probability of interest, and then we prove that Q of 2n is upper bounded by what we want plus something which is smaller than half times Q of n. The quarter has no significance other than being strictly smaller than half. So then iterating this inequality, you get that Q of n is upper bounded by some other constant times log n to a third divided by n. And in order to do this, this dynamical way of generating the uniform spanning forest is very well suited for this type of inductive inequality. So the way we prove it is by, so in the lower bound, we ask that 0 was hit by a unique trajectory. So now we're going to consider two cases. Either 0 is hit between time 0 and epsilon or not. If it is not hit, okay, so I guess I don't have enough time to explain this argument briefly, but I just want to say that for the upper bound, we need control, we need a very good control on lower tail estimates for the capacity of the first n steps of loop erasure, and this becomes much, much harder. And in order to analyze this, another important ingredient of the proof was to use some tools that I developed in earlier work with Amina Salah and Bruno Shapira, where we studied the capacity of the first n steps of a simple random walk. I'll stop here just by having the slide. It's the result that I mentioned earlier. So thanks a lot.
Thank you very much. Any questions? So I have one. So for the lower bound, so you defined this fancy FT on random interlacements, and so for the lower bound, you could choose whatever T you want in order to get the estimate, right? So the probability that some path is in the set is larger than the probability it is for a certain. So you took like 0 epsilon and then you chose epsilon. So is this right? This is why it's only, you can only do this for the lower bound?
Okay, so for the upper bound, so let me say that this sequence FT is a stationary sequence. Mm-hmm. So for the upper bound, the way we do it is, so remember, we want to relate this Q to N. So we want to know what is the probability that the radius of the path after time 0 is greater than or equal to 2n. So we split it into two events. Either the first trajectory arrived before time delta, or the radius is greater than or equal to 2n, and sigma 0 arrived, and the first trajectory arrived after time delta. So now we have to look at both terms. So for the first term, in high dimensions, Tom simply upper bounded this first term by this event, and this event has probability of order delta because it's a Poisson process. And for high dimensions, this was good enough because the delta that you need to take is of order 1 over n. Here, the delta that we need to take from this term is again going to be log n to the 2/3 divided by n, because you have to kill an exponential term with a capacity like before. So if you take this delta, then this bound here is not good because it gives you an extra log n to a third term. So we had to work hard also for the first term. So for the first term, it's proving kind of a converse inequality to what I proved before. So we show that this is indeed log n to a third divided by n. So now we have to understand this second part. And it's here that you see how we use the dynamics. So we want the radius of the path after time 0 to be at least 2n. So just very briefly, suppose that 0 is here, this is the path. So if you want the path to go up to distance 2n, there are going to be vertices that are at distance exactly n from 0. So when I say distance, I mean in the tree. And V will also have a path that reaches distance n. So now, since V is in the path of 0 here, and this is of length n, now this path here, this path between 0 and V, it cannot have been hit by any trajectory of random interlacements in 0 delta. This is because V was hit later than 0 because V is in the past. 0 was hit after time delta for the first time. So in particular, V was hit after time delta for the first time. So then if there was a path coming before time delta, this would mean that V would no longer be in the past of 0. So then what we can do is we can upper bound the probability that V is in the past of 0 after time 0 at distance n. Let's write it like this. And the past of V after time 0 has large radius, and sigma 0 is greater than delta. We can upper bound that by the probability that V will also belong to the past of 0 after time delta at distance n, because this path cannot have been hit for the reason I said before. And so in particular, V will also depend to the past after time delta. And then similarly here, so I can just replace delta here. And then I'm going to ask that if I call this path gamma 0V intersection the interlacements in 0 delta has to be the empty set, because we don't want it to be hit by any trajectory. So now, how does the capacity come into play? We're going to consider two cases here, depending on the capacity of this path. So if this path has large capacity, so the large, I mean larger than n over log n to the 2/3 times the right constant, then we're going to get the exponential term like before, and then we can easily bound everything. And so now the issue is, if the capacity of this path is smaller than what it should be, and this is the term that we need to control. So this is why I said we need to understand these lower tail estimates for the capacity, because these paths, they're paths on the uniform spanning tree, so they have the distribution of loop arrays walks. So we need to, so it boils down to understanding the capacity of loop arrays paths.
Okay, thanks. Any other questions? No, so let's thank Perla again. And see you all next semester.
Thank you.
Thank you.
Thank you, Perla. It was a wonderful talk.
Thank you.